เขาพูดแบบนี้ก็เลยต้องถามแต่ว่าเยอะมากเราที่เราไม่พอมาดูเรื่องคือแต่ก็ชอบไม่มีใครเขาก็ดูเรื่องไม่ได้ไม่ได้ให้เขาออกเลยแล้วมีอะไรยัง
You have got. You have joined. Have you joined? No, not yet. So when will you have to defend the topic or propose the topic for this course? When will be that schedule? Next week? Next month? Okay, you still have some time next month. Okay. During this time, then try to explore one topic that you would like to work on for this course. And if possible, if you would like to continue this topic now for your thesis as well, that it should be very good. Okay. If you have got no idea, just try to catch me or try to catch Ajahn Kamrat. If you have no idea during this time or next week, and you may need to talk with Ajahn Kamrat or myself in order to get to talk. Okay. So we would like you to work on your thesis as soon as possible. So the topic for the IAC 603, if it is the same as your topic for thesis, and that should be good. All right? Okay. That open data and read the data down for one. Okay, good morning. Let's start. All right. Today I will talk about how to analyze data, applying treatment effect model for emulate clinical trial. Okay. So that what I'm going to cover the treatment effect model analysis for the outcome, binary outcome, and then I will move to time to event outcome. And if I have got time left, and then I will cover continuous outcome as well. But if I don't have time, and then you can study by yourself because it's quite similar with binary outcome. Okay, if you remember last that was in study design, right? In study design, the ISA 622 that I talked about the study design, how to construct and develop the study design for emulate clinical trial that I did talk about that already. But today I will focus on, can you post it on? I will now focus on only analysis. All right. So, R1 Himalata. Do I pronounce it correctly?
You can call me Hema.
Let's say again.
Hemlata Krishna.
Himalata. Can I call you Krishna? Is that your surname, right?
Yeah.
Okay, which one is?
Hema.
Yes. Hema.
Yeah.
Okay, nickname Hema. Okay, that's better. All right, and ณภัสกรอาจารย์นะ and who? Hugh. June. Okay. But how to pronounce your first name? Hui. Okay, Hui. And then oh wow, what is that name? Pan. I can't pronounce your first name. Xiao. Jue. Can I call you Pan? Yes, much easier. All right, so we have 1, 2, 3, 4, 5, 6 students currently. And I think I should lock the door because this time 9 o'clock already. Okay, let's start with analysis for binary outcome. So that we apply the treatment effect model that can assess the change of the outcome value. The change of the outcome value that solely caused by individual patients who receive one or another treatment. But this treatment effect model at individual patient level cannot be directly observed because each patient actually receives each treatment at each of the time. They cannot receive two treatments at the same time. And therefore, the counterfactual approach is applied to estimate the treatment effect for individual patient. Now, when the patient do and do not receive that specific treatment. The counterfactual approach means what if. Now, what a result of individual patient would be if that patient receives another treatment instead of the current treatment. For example, currently the patients receive the drug GLP-1RA for diabetic drug control. What fasting blood glucose or hemoglobin A1C would be if that patient receive DPP4 instead of GLP-1RA. Okay, this is the meaning of counterfactual approach or vice versa. So that now we working on the actual observe of observed outcome if the patient do not receive the treatment that we assign as why not, and their outcome would be Y1 if they receive treatment. And the Y1 is the potential outcome or the counterfactual for these patients. Okay, if the patients receive DPP4, that is why not. And the new or the more expensive one, GLP-1RA. Now, if these patients who currently receive DPP4, but if they receive GLP-1RA, now how their hemoglobin A1C would be, that is Y1. Okay, and the patient who do receive the treatment, their actual Y1 are then observed. And why not would be the counterfactual outcome. And then we can calculate the differences between Y1 and Y0. And we call now Y1 and Y0 as potential outcome. So how to calculate the differences between Y1 and Y0? And that now we need to construct the two models. The first model, that is the treatment model. So how to construct the treatment model? And that from this equation, you can see the left-hand side, that is Tij, that is the treatment. Okay, Tij. Now the treatment of the person number I, the patient number I, and the J treatment. Okay, that is the subscription. Equal the summation of equal beta naught plus the summation of B1x, B naught plus summation of Bixi. Okay, Bixi. So that this is the treatment allocation. If you perform clinical trial or randomized control trial, the patients would receive treatment GLP-1RA or DPP4, and that based on randomization for clinical trial. Okay, based on randomization. For the real world practice, it depends on the conditions of the patients and depends on accessibility to treatment in terms of the health insurance, and also it depends on the decision of the doctor who look after the patients. Okay, so that is not randomization. So we try to gather Xi, that is the covariance that now the characteristic of the patients, characteristic of the underlying diseases of the patients, and also the health insurance now include in the model now in order to predict the treatment allocation. Okay? In order to predict the treatment allocation. That is the meaning for the treatment model. All right? And then now we work on another outcome model, two models, the outcome models. So the outcome models that is the Y1 and Y not. So the outcome models, it depends on what outcome that you are working on. For example, if we work on hemoglobin A1C as the outcome, or we're working on systolic blood pressure as the outcome. So the left-hand side, that is the Y, and Y not, that is the comparator. Here is the PP4, for example, that just provide you the example, the PP4, and Y1, that is the outcome now or in GLP-1RA. Okay, and then we look at what characteristic of the patients and also the health insurance, if any, and other underlying diseases of the patients that associate with the outcome. But we stratify the outcome model according to the group of the treatment, Y1 and Y not. That is the outcome model. And then we need to estimate the three parameters. Now when you work on the treatment model. And the first one that we call the potential outcome mean. So why potential? Because now we apply the counterfactual approach, and that the actual observed, that is the factual, and the counterfactual, that is the unobserved outcome. So if the patient receives DPP4, that is the observed or actual outcome. And then the counterfactual, if that patient receives GLP-1RA. Okay, so that's what we call potential outcome. Potential outcome means, and then we work on the potential outcome mean for each. ไม่อนุญาตให้เข้าพี่ไม่อนุญาตให้เข้า9 โมงค่ะไม่อนุญาตค่ะบอกไม่ต้องเรียนเลยค่ะไม่ให้เข้าค่ะทำไมสับสนได้ยังไงคะบอกอาจารย์เขาโทรมาคุยกับพี่ไม่อนุญาตให้เข้าไม่ต้องมาบอกไม่ต้องมาค่ะ9 โมงคือ9 โมงค่ะ Okay, so that the potential outcome mean that is the Y POM, potential outcome, mean the expectation of the outcome. And then we can work on the average treatment effect. The average treatment effect. What does it mean here for the average treatment effect? If you can estimate the Y1 and Y not, and subtraction Y1 from Y not, and that is the risk reduction, right? The differences between the two outcomes, that is the average, that treatment effect. The average treatment effect here. So the average treatment effect, Y1 minus Y not. And then now you can look at the average treatment effect in the treatment group only as well. Okay, but basically we need to estimate at least two potential outcome and the average treatment effect. Okay, and then for data analysis by data analysis by data that we are going to focusing on more and more now for today, and we for the binary outcome that you can work on regression adjustment. For in data, the outcome models that we can apply regression adjustment. For the treatment model, we can apply the inverse probability weighting or augmented inverse probability weighting.
Now, there are two techniques for the treatment model: inverse probability weighting and augmented inverse probability weighting. And then another treatment model we call propensity score matching. Propensity score matching. Now, you may have heard a lot in the articles. This technique is very, very popular for propensity score matching. Okay, and then now you will learn how to do now for propensity score matching, and that now based on the treatment model only, and estimate inverse probability weighting, and then use that probability weighting to match between intervention and control or treatment GLP-1 and DPP-4, and the ratio can be vary. The ratio can be vary. It depends on if you have more number of the patients for DPP-4, and then you can vary from 1 and 1, 2 and 1, 3 and 1, 4. But if you have GLP-1 RA more than number of DPP-4, so it can be 1, 1, 2, 1, 3, 1, 4, 1. Okay? So the situation for the ratio, because we want to increase the power. We want to increase the power and utilize the data as much as possible, so that it depends on the number of the treatment of interest and the control that available in your data set, and then you can justify properly which ratio you will go to. Okay? The best technique, you can see that I talk about the treatment model only, the outcome model only. And then we can combine two of them together that we call doubly robust method. Doubly robust method. So that means not just only the treatment model that we are going to construct, we also construct the outcome model as well. Okay, combine them all together, and that this technique is also now very popular. We call inverse probability weighting with regression adjustment. So both treatment and outcome models are constructed, and that try to include the covariates that associate with treatment allocation, and the covariates associated with the outcome occurrences. Okay, and the covariates of the two models are not necessarily to be the same. Okay, you have to justify about the treatment allocation, and you have to justify about the mechanism of disease in terms of the covariates and the outcome. And both models not necessarily to be the same. And then we construct the treatment model first in order to estimate inverse probability weighting. Okay, and then you will know later what it means for inverse probability weighting here. And then we construct the outcome model by fitting by weight regression, fitting weight regression. And given the weight equal 1 over P for the treatment, and 1 over 1 minus P for the comparator to obtain the treatment specific predicted outcome. And after that, you can estimate the potential outcome mean, and then subtract the two of them or divide the ratio two of them, and then you can come up with average treatment effect or the ratio of two potential outcome mean. Okay, let's move to the data that now we are going to focus on for this session, and also the next section as well. That it is about chronic kidney disease cohort. Chronic kidney disease cohort, and that now the treatment of interest here, that is the RAS blockage. The RAS blockage, okay, the RAS blockage. So that the RAS blockage, renin angiotensin aldosterone system, renin angiotensin aldosterone system blockage. And we know that now for this RAS blockage, including now the A or B or the S inhibitor, and this kind of medications have the effect we call renal protective effect, and that can delay the kidney progression, CKD progression, can delay CKD progression. And this kind of medications that strongly recommend in clinical practice guideline for chronic kidney disease patients. In order to delay CKD progression from early stage to higher state of CKD or chronic kidney disease. CKD abbreviation, chronic kidney disease. And then the outcome is death for this data. And we have covariates here that I list not too many, but not too small number, including age, gender, BMI, diabetes, and hypertension, the history of cardiovascular diseases, and the LDL level, the HDL level, and urine albumin. So these covariates will be considered to construct treatment model and the outcome model. Okay, let's take a look at the step of analysis. Okay, look at a step of analysis. Okay, let's move to data and open the data, please. Okay, let's take a look at the covariates that I just mentioned. Age, 6 2, and BMI on the variable predict predict to underscore BMI. Okay, let's take a look together. Okay, the variables age are 6 2 and BMI, DM, hypertension, CVD, HDL, LDL, and urine albumin group. Now, of these 9 variables, let's explore the distribution. Explore the distribution between the treatment group. The variable for the treatment group are RAS2. I think RAS2. Yes, it's called RAS2. Let's separate RAS2. Okay, so that about 42.7% of the patients, CKD patients, receive RAS2, and the rest did not receive RAS2. Okay, so that let's take a look at the distribution of these 9 covariates. Now, whether these covariates are different between the 2 treatment groups or not. These covariates are different between the 2 treatment groups or not. So that we start to build up the treatment model by performing univariate analysis. When you do univariate analysis here, you can work on very simple technique. For example, if age, that is continuous data, you can compare mean between the 2 groups. If gender, that is categorical or binary data, you can tabulate and then now look at the proportion. And then now assess now whether the two proportions now, but the proportion of males in now RAS bucket compared to males in non-RAS bucket are different or not. Okay, so that you can work on really simple like this. Don't jump to now logistic equations straight away. Okay, I strongly recommend to work on really simple analysis and let you understand the data. Let you understand the data and also now explore the distribution of each covariate and the other treatment variable. And then you can see the possibility to fit the model. Don't jump to fitting the model without inspection of the data. All right, so let's do very simple way. Now start from age, sex, and BMI, DM, hypertension, CVD. So what if you construct the dummy variable here, now typically here that is the factor of patient's characteristic, okay? And then you have RAS blockage and non-RAS blockage. Okay? So this the dummy table that you need to construct. And normally, now when you work on or when we read work on randomized control trial, that now in order to explore and assess now the treatment allocation or randomization work well or not, so that we need to test the characteristic of the patients between the two treatment groups. Okay, that is typical for randomized control trial. Here is the same for IMLET trial. It is the same. So that we have the treatment of interest, and we have the characteristics of the patients here, and then we export the distribution between the two treatment groups. Okay, and then you can see how balances or unbalances of these covariates between the two treatment groups. All right, and you can see the expectation very small differences or very big differences, and then you can now work on the treatment model step by step. So right now please work on this table. Start from age. Age is continuous data, and then if you don't want to categorize, that is fine. But if you want to categorize, you can do as well. Okay, but if here the unit is year, right, and then mean, and then SD. This is the way to report, okay? This is the way to report. So now we start with the variable and unit, if any, and then the parameter that we want to report here is the mean. And in the bracket, that is the SD, okay? And then you can report mean age for RAS and non-RAS. And then you can now report p-value as well here, p-value. All right. And the thing is that you need to add n equal. So from here that now for gender, that is categorical variable, right? 6. And then you set number and percentage. And then you have males and then female, right? This is the way how to report the data. The same for other categorical variable. You do similar to this gender, okay? But the percent here must be the percent according to the treatment. All right, percentage according to the treatment. Because the treatment here is our study factor. If it is randomized control trial, that you need to look at characteristics of the last blockage and non-last blockage. Okay, and that must be the percentage according to the treatment group. And similar to the cohort study, the treatment of interest here is the exposed and non-exposed of interest, so that the percentage must be according to the exposed and non-exposed. So when you report the data, justify carefully according to the study design, now which percentage that you have to report, okay? This report correspond to the study design. And then you have hypertension, you have BMI, right? BMI. And what is the unit of BMI? kg by m square, and then mean, and then SD. Okay? And the rest that you can decide by yourself properly. So right now let's work on the data, and we have DM, we have hypertension, and we have what else? The LDL, right? We have CVD, we have LDL, we have the HDL, and we have urine albumin group 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's do together and tell me now which one. This is univariate analysis, okay? And you can add the odds ratio as well, and 95% CI if you want, but p-value should be fine for this, not necessarily for the odds ratio. Okay, so let's do and tell me the p-value for each covariate, and then we go to the next step, that multivariate. For this part, that we try to collect the covariates that might be associated with treatment allocation. That is the meaning. Okay, that associated with treatment allocation. I didn't bring the health insurance to this data because this data came from the health insurance that we call national NHSO, the National Health System, universal coverage, let's say, universal coverage, only one source only. So for the treatment allocation, no need to assign the health insurance. But if you work on other treatment and the data from different sources as well, and for example, if we work on the cohort in Ramat Hospital, and now we have different type of health insurance or payer, so that you may need to fit the covariate health insurance into the model as well. All right. Okay, tell me now which covariate that should go to the next step. For this step, the covariate that p-value less than or equal 0.1 should go to the next step, multivariate analysis. Okay, and the threshold p-value 0.1, p 0.1. It can be 0. Or even higher, 0.1. It depends on how big the data that you have got in hands, and also how many covariates there are. If you have not too many, and you have got big data, and you can increase the level, the threshold here. Okay, but if you have a small number of the data, you may stick at 0.1. Okay. You can justify the threshold of the p-value for this part. And the next step that we need to include the covariates that now pass through this condition, and then we fit them in the multivariate for the next step. This is step number 1. And step number 2, collect these covariates, consider simultaneously in the multivariate model. And it depends on which approach you are going to fit in, the forward selection or the backward selection. Okay. Ba Cindy later. Okay, tell me which variable should go to the next step. Mean age. $62. 0.08, okay, 0.1. Only one decimal. And the SD. 11.5. Well, non-RAS package. 64.6. And the SD. 13.7. Okay, the p-value. Less than 0.001. Okay. All right. How's about the how's about gender? How's about gender? Pan. Gender. Pan do gender. And Hema. Can you do BMI, please? Hema. And Napasakon. Can you do DM? Uraiwan, can you do hypertension? And Omo, can you please do CVD? And can you do the LDL? And if you finish what I assign you, and then you can do HDL and urine albumin for me, please. Okay, good morning. So what's your name? Pontisha. Okay, sorry about the miscommunication, right? Sorry about this. Yeah, actually I start 9 o'clock in the morning. Just in case that I'm not available in the morning, so that I will start about probably on Thursday. You look at the schedule carefully on Thursday, 1:30, I think. But please check the schedule carefully, all right? And be on time, please. Good morning. Chavarat, okay. Tivat, Pon พิชยาพรพิชาชนิกตาชนิตานัทพงศ์เอกกี้ no he's sick so what's happened with him no idea diarrhea or flu or sick ปิยธิดา andรุ่งมน okay all right let's turn on the data and read the data please turn on data and read the data that we already allocated to you have you got the handout and data so sorry about miscommunication between our staff and your staff. So you thought that the class started 9:30. Oh, that was. But the schedule is 1 p.m. or not? The schedule is 9 or 1 p.m. Sorry about this. Yeah. Sorry about this. Yeah. Don't know which version for that. Sorry about this. Okay, tell me for gender, please.
Gender for the female, they are with RAAS number is 5,189.
5,400.
189. 180.
189?
Yes.
189.
Yes.
What the percentage?
Okay. The percentage is 95.81.
95.8.
81.
Okay, 0.8.
Okay. So for those who don't have the RAS, non-RAS, the number for the male is 227. 227.
227.
Yes. 227 for male without RAAS, non-RAS.
Can you take a look at the layout and tell me exactly what the number here? This is female, right? In the last package.
5,000, this is for male.
5,000 for male?
Yes, for male for male there have RAS. Yes.
Okay, this is male and this is female.
Yeah. For the female is 10165. Number is 10165.
Should be 4.2 according to this.
Yeah.
For the male, this is number.
Yes.
So this will have now
Okay, why don't you just try to complete this group by group first? 5189, and this is for the female. So what the percentage of male? What the percentage of male?
The percentage for the male is 4.19. 95.8.
95.8. Okay.
So for the male, the school now IS is 227.
227. What the percentage?
The percentage is 4.1.
I don't think it's correctly. I don't think so. Can you work on your data? Exactly. Now this male in the row and the treatment in the column. If you work on, it doesn't matter if you work on the treatment on the row, and so you lay out differently. So this is okay, but you need the row percentage. You don't understand suggested. Good. Okay, normally we going to report this kind of table, okay? This kind of table. You just hit the tablet command exactly the same as this layout. All right. So the factor of interest on the row and the treatment on the column and the percentage according to the column, not the row. All right. If you want to now tap another way around, now the treatment now on the row and the factors on the column, that is okay. But it must be the percentage according to the row, because we have to report the percentage according to the treatment group. Because the study design, according to the study design, is similar to cohort study. Okay? So you just lay out, if you want to do exactly the same as this table, the factor first, here it's gender, right? Tablet, gender. And then follow with the treatment RAS. Okay? So tablet, sex 2, and then RAAS, and then column, and then Chi2. That's it. And you pick the percentage. You can pick the percentage here. 33.8 for male in RAS package, and 35.9 in non-RAS package, right? Don't mix up now what you should report and the percentage according to row or column. According to row or column, it depends on how you lay out now the tablet command. All right? How you lay out the tablet command. So do properly. And I just said that now when you're going to report the percentage, because at the end that we want to look at, now how different of the percent male. How differences of the percent male. This is about 33. This is about 35, right? But you need 1 decimal point. So whether the 33 and 35% are different or not, that is based on the null hypothesis. What is the null hypothesis here? The two proportion, right? Not different. What are not different? What are different and what are not different? P1 equal P0, right? P1 male equal P0 male, right? The percentage of males in last package equal the percentage of males in not last package. And you can see the point difference 2%. The point difference. Whether 2% is statistically significant different or not, that you have to apply. So what type of test? The chi-square test. Right, the chi-square test. That tests for the two proportions. So what's the p-value here?
0.269, 0.27.
0.27. One more decimal for the p-value usually reported as 3 decimal points. Yeah, for p-value. 269. 269. Okay. So the two proportions are not statistically significant different.
Excuse me, Ajahn, we have to use the last two or variable. Yes. In the command, Ajahn use last, but I'm not sure we have to use last.
Yeah, last two, please. Last two.
Thank you so much.
The last two. Yeah, 33 and 38. 33.3 and 38.8. 33.3 and 38.8%. Yeah, last two. Okay. Very much different. Yes, very much different. Because now this at least 5%. Yeah, at least 5%. So the p-value less than 0.01. Okay. Okay, next. BMI. $23.78, 4.1, 21.8, 4.2. Okay, what is the null hypothesis here? Okay, that is the mean of BMI in 1 equal to mean of BMI not. So what is the p-value? 0.001. What type of test did you apply for? T-test? Independent t-test or pair t-test? Independent t-test, equal and equivalence. Did you test the valence first? The default is equal and equivalence. Equivalence. You have to read in the help file the default of t-test, whether it is equal and equivalence. So the p-value 0.001. Okay, next, diabetes. Yes.
And the percentage is
66.0.
5,981. And the percentage is 32.
Yeah, I think it might be another way around. Is that? Nah.
Of them so positive is 4,657.
4,567 is the last blockage. Yes.
For negative and EM positive. 5,981.
5,981. 981,
32.5
32.5%. And
for positive RAS and DM positive is 9,051 and 66.0%.
9,551. Okay,
And percentage is
66.0. All right. Huge difference. Huge difference.
And for the negative, positive IAS is and DM negative is 4,357. Sorry. And for P value is below 0.001.
Okay. Okay, this significant 0.001 less than. All right, for hypertension,
non-hypertension in less positive is 9,051.
9,051.
Yes, and the percent is 66.0.
Are you sure? This is 9,551 equal percentage.
Sorry, I read the DM result. Okay, can I change right now? Yeah.
Yes. By this course, you have to be now very quickly and handy with a data command. Okay.
Yes. And again, please, 8,624.
8,624.
Yes, the percentage is 62.5.
62.5.
For the negative blast is 18,000.
18,000.
300. Oh, so sorry, Ajahn. 5,177.
Say again, please.
5,100.
5,100.
77.
77. Okay.
The percentage is 37.5.
37.5. Okay.
For non-hypertension in
No, just this should be okay.
For the p-value is lesser than 0.01.
Okay. And can you repeat DM again, please? I think the number is odd to me for DM. DM, please. Can you provide me the number again? It looks very odd to me for DM here. For RAS package.
Yes, is 9,051.
9,051. Okay. Okay. And for non-RAS package. 5981.
500,000 with 981.
Okay, 32.5. Okay, good. All right. For CVD.
For CVD, the positive one is 1,930.
1,930.
And it's 14.1%.
14.1.
And the other one is 2,441. And the percent is 13.3. And the p-value is 0.036.
0.036. Okay, good.
Next for LDL, mean 113.2.
113.2.
13.2. 32.5.
32.5.
sorry. For the rust, for the hair rust, 117.9.
170.9.
17.
17. Okay. 17.9.
And now 41.3.
41.3.
And I use the t-test with the unequal variance and p-value smaller than 0.0, smaller than 0.01.
Okay. For the HDL, Chanita, please. Chanita, can you tell me about the mean HDL in the RAS package, please? Please. Rungmon, can you please tell me for urine albumin group? Too many value? Okay, let me take a look at how you did. Okay, you tablet the predict the LDL and okay. So you use the tablet command for continuous data. So that's why data upset you and say too many values go. Too many values go. So the tablet command for categorical variable. All right, but the LDL is continuous variable. Okay, the LDL is continuous variable, so that's why data said, oh, too many values. So we need to compare the mean, right? For continuous data. So that we want to compare the mean of the LDL between RAS and non-RAS package. So what is the command? T-test, right? Yeah, hit T-test. Did you study 625? No. Oh, did you study basic biostatistics or not?
But not here.
Okay. Okay.
Also about the basic data.
Basic data as well. So that you need to only 3 hours or one courses? No. 1-2 classes. Okay, I'll with your Ajahn phone that. All right. So we need to test two means. Omo, can you tell your friend? Yeah, that's okay. That's okay. I can't cut and paste. Yeah. Which one? This one, right? Yeah. Yeah. Yes. For the continuous variable, we need to test two means, and that we apply t-test, right? T-test. Rank sum? Okay. So how's the data? How's the distribution? Okay. But it's not too bad actually. The mean is 38.9 and now SD is 9. About 1/4. Yeah, about 1/4 of the mean, which is not too bad. And another group is 39 and 11. Okay. Let's say about 3.5. Yeah. So, but the data is really kurtosis, but not too skewed. Now the skewness is not too bad at all, but the data is really kurtosis. So if you test normal distribution, it should be violated. if you test normal distribution, but it's still not too bad. What does it mean from here that if the data is very corrosive, like this, but now the skewness is still okay, but the corrosive. But if the skewness is now very skew left or right tail, this is right tail, and this is left tail. If the data is very skewness, that you need to test, compare the median. But this mean is still okay. But if you test normal distribution, of course that now probably not pass the assumption at all. Okay. No column. You see, you have only one variable. You have only one variable. Need two variable.
Okay.
So you read carefully what data told you, and then you know straight away. Okay, this is okay. So what is the mean of HDL in the RAS package and non-RAS package? Tanita. Mean HDL in the RAS package.
HDL in the RAS is the HDL is 38.96.
38.96. Okay. Let's say 39. We need one decimal point, and the way to report one decimal point that we round up is now the decimal 0.5 or higher, and then we round up 39.8, right?
Right.
39.8, and what is the second decimal point?
Second is the second of IS is the I will show you.
No. I can walk to there. Yeah, you sit there. Predict, okay, RAS package, so that 39.1. Yeah.
So we just
And
use
then
only one.
One decimal, and this is 38.9, but before 9, the second decimal, 6, you round up, and 9, 1, and that is 0, right? And that is 39, 39.0, and 39.1, okay? That is the way how to report. The 39.0 and the SD. So what is the p-value?
Uh, 0.17. So is the 0.17 here.
The third decimal?
The third is 8. Sorry, 0.18.
No. We have to report 3 decimal points.
It's 0.17 and 9 because the fourth digit is the 9. So I
Okay, 180, right? 180. 0.1. 0. Is that correctly? For the HDL, I don't think so. Is it correctly? For the HDL, 11.4. 39.0. 9.0. The p-value? 0.194. Why? Why you come up with different? The last two. Which one? Okay, 0.194. 0.194. We test two-tail test. It can be either way. we test the two tails. P-value 0.198. Two-tail test. Okay, the last one, urine albumin group, please. Natapong, please. Natapong. $5,332. 43.1. And another group, please. 7,000. And then 38. The percent. 56.9. Okay, the p-value 0.24. Are you sure? 56.9 compared to 43 must be statistically significant. Okay, we need the percentage according to the column, okay? It doesn't matter if you lay out row or column, but you need to specify the percentage correctly. But if you don't want to error, you just lay out on this way, okay? Yes, please.
The percentage.
Correct. Incorrectly? Okay. What is the correct one? $38.2. Okay, 0.3. About 10, 8, 9, 10, 5% different. Okay. 38.9. Okay. So the p-value should be now. Yes. 0.24. All right. Okay. Is there any question according to this? Ask me before we move forward. And I told you how to lay out the table, how to report the table, okay? So now learning from here, and that should be able to apply to other courses in your proposal and in your thesis in the future. This is the way how to report. If you conduct randomized control trial, or if you conduct a cohort study, the way to report characteristics of the patients by the treatment groups or by the exposure of interest is similar. But if you run the case control study, and then you started now with cases or diseases, and then you look for the control without diseases. All right, so that is the start point. You identify the patients now with the disease of interest. For example, if you identify the patients with COPD exacerbation or COPD exacerbation, and then now you look at the control now without COPD, for example. So the percentage must be based on the disease and the control for case control. All right. But the cross-sectional study, now when you conduct a cross-sectional study, that is the survey study. So on that time, at that time that you survey and you collect the data, and the patients report to you that they now have chronic kidney disease, for example. And they might know on that day, or they might know before then. And then it can be new cases, and it can be the old cases. Now the patients might have CKD before, but on that day that they assess serum creatinine and convert to eGFR and eGFR lower than 60, for example, by function. And then that patient might have chronic kidney diseases. Chronic kidney disease now that detect on that day might occur before, but the patient somehow or another they do not have the chance to do the test. And that can be the old and the new cases. That's typical for cross-sectional study. Okay. So for cross-sectional study, you can report the data like this, or you can report the data similar to case control study. All right. Any question from here? Okay, let's move to the next step. Now, collection form this univariate analysis that this should go to the next step, right? And this should go to the next step. Yes, gender. And then BMI should go to the next step or not? BMI. Some yes, some no. So are you working with the same data? Are you? Aren't you? Some yes, some no. So what do you mean? Yes, right? Okay, BMI. And then DM. Yes. Hypertension. Yes. CVD. Yes. DLDL. Yes. DHDL. No. No. Okay. So the first step that we work on univariate analysis, and then we collect the variables whose p-value 0.1 or lower in order to consider in multivariate analysis. Okay. We won't use 0.05 at the beginning. That is too strict criteria, because right now that we want to explore the potential factors might associate with treatment allocation. We are working on the treatment model. So from this step, now 9 predictors, so that's 7 of 9 that should go to the next step. So which way would you like to do, backward elimination or forward elimination? For this huge number of sample size, 32,106, and with the percentage of having RAS blockage and non-RAS blockage nearly equal, 40 to 50 something. So shouldn't be the problem in terms of number of event of interest, that is the RAS blockage. Given huge total sample size 32,000 approximately. So you can, and given that all of them have no missing data, all right? All of them 9 variable have no missing data. So now you can do stepwise. You can do backward elimination, or you can do forward elimination. If some of them have missing data, and if you do backward elimination by including 7 of 9 into the same model, and that the sample size will be reduced from 32,000. Okay, so that you need to be careful and justify carefully when you work on model selection. And so therefore you may need to do forward selection by enter one by one. And for this step, that either forward selection or backward selection, if possible, that please do manual work, not just ready-made command and that you can understand how important now for each variable. Okay, let's do together. So which one is the most significant variable? You have to look at the p-value because you cut off lower than 0.001. So you don't know now which one now has the highest p-value. Stata usually report only 3 decimal point, but if you work on like return list, and then you can see p-value from there for the tablet one. Can you see the p-value? DM? So what is the p-value for DM? Yeah, so it should be like minus. Can you see on the screen here that I tabulate the gender and the last blockage? Okay. And if I use return list, data storage p-value there, so you can see the RN and the RR and the RC, that is the column and the row. And the R chi-square 102.7516, and the RP value of that chi-square 3.80 multiplied by 3.80 multiplied by 10 over minus 24. That is the meaning. Okay? You can see that 3.79991555419 and E and minus 24. It means 3.8 multiplied by 10 minus 24. That is the p-value. That is the actual p-value. But when Nastera reported not only 3 decimal point, and it is 0.000. But when you report, you should say lower than 0.001. Okay. So you can justify by yourself. Now, if you want to do forward selection, you enter the most significant variable. You have to collect the p-value and then enter the most significant variable into the model, and then the second. And if adding the second now with the first one, more significant, now whether it is significant or not, if significant, remain that variable and then add the third one and so on. But for the forward, this is for forward selection. And you use a lot now for forward selection. But if it is backward selection, now very easily log it last to age, right? 6 to. You can add now I dot. But here that we have got only now only 2 groups, it doesn't matter, but you can add as well I dot 6. And then what is the next one? BMI, right? Predict underscore BMI. BMI, okay, predict to BMI. And what is the next? DM. And then hypertension. With or without I dot, it doesn't matter because you have only 2 groups, okay? And then CVD. And then predict LDL. And then the last one, No, just read this, right? 7 of them. So this is forward selection. You fit with the full models and then you eliminate one by one. That is now backward selection. Now you fit all of them and then eliminate one by one. And can you please tell me if you can eliminate each of these or not? This is a full model. All right. If you want to eliminate the LDL, what is the p-value? And what type of test that you would like to apply for? The concept is similar to now when you work on prediction model. When you work on prediction model, that build a prediction model that you need to select now the variables carefully. So what type of test here that we are going to now work on backward elimination, not forward elimination. The LR test, all right. So how to do the LR test? Okay, estimate, store, full, right? Okay, and then we eliminate one by one. Estimate, store, full. This is a full model. This is the full model. And then enter. And then page up the same model and then eliminate predict LDL. Shall we? And then predict LDL and then estimate store LDL and then compare the full and the reduced model by reduced LDL. And that the likelihood ratio tests. All right, page up and delete the LDL and hit the command the same. Okay, estimate store. Estimate store. Whatever name that you want to name. Whatever name that you want to name. Yeah. Okay, and estimate store LDL. Okay, and then omit LDL. All right, and then next. So no. Would you like to apply the LR test? Full and the LDL. Okay. So there are two tests for model selection. Now each of covalent. One is the likelihood ratio test, and the second the Wald test. And you can see that the Wald test now in regression table, the standardized normal test, that is the Wald test, along with the p-value. But sometimes it's not sensitive compared to likelihood ratio test, so we prefer likelihood ratio test rather than the Wald test. And then enter. So the likelihood ratio comparing the log likelihood of the full models and the reduced model without the LDL. And the log likelihood of the two models are statistically significant. And that means including LDL is meaningful, or in other words, excluding or omitting the LDL are increasing the log likelihood. So we should keep the LDL. Okay, so next do the same, include the LDL, but omit the second one from the full model. CVD, But don't forget to include the LDL, okay? Because we want to see eliminate each of covariate, each of the time from the full model, whether it is significant or not. DVD. Okay. The problem, there might be the problem according to, can I have a look at the full model, please? Yeah, the full model. Okay, this is the full model. Can you re-estimate, estimate store, estimate to, no, estimate store and then full. Store. And then full. Okay, enter. And then can you apply 2T106? Can I have a look at the model that you drop out? You drop out. No, you shouldn't drop full. You shouldn't drop full. Okay, let's do the LDL. Omit the LDL. Can you page up the full model? Page up the full model. Page up, page up. No, you can click on the full model here. Okay, no, this is okay. You omit LDL and hit the command. Yeah, enter. And then estimate store LDL. LDL. Okay. The LR test, please. LR test. And the full LDL, yes. Okay. And do the same. But you be careful. Make sure that you reduce the model properly. Don't reduce two variables at the same time. Because if you want to test that, eliminate each of covariate. Yeah, delete CVD. Actually, instead that you can now take note for your understanding as well. Now, for example, that you omit CVD for this model, you're going to omit CVD, and then you note here like omit CVD, okay, and then page up the full model and then delete CVD. All right, and then estimate store CVD and then LR test CVD. Okay, or you can work on do file and write the command step by step. Question? Okay. But seem to be question. No question. No. Yes. No, that's okay.
In the slide will ask you that in this we just test the we test that if with or without this factor, the prediction model will be like or not, right? And we will try by okay, if without red LDL,
Yes.
is will be good or not? So I said will without CBD because I will.
Are you confusing?
Yeah.
No, you can do this again. Make the right name. Estimate store LDL.
So we would like it out and we would like to be compared with the full model, right?
Mm-hmm.
So can I use the model name?
Well, it's okay that you just estimate now based on the current model. Yeah.
Because I save the model, not name, not full, but with LDL. So
Can I replace the model name to be full model? I'm not sure you can help now. Otherwise, you can just redo. Yeah. If anyone would like to do prediction model, you have to apply this technique, okay? For the prediction model. It is okay. It doesn't matter for the step from the backward elimination. Now, well, right now that we have 7 variables in the full model, and we question if we omit each of them, now whether that the reduced model after omission, reduced model compared to the full model are different or not. Okay, for each variable. Okay, so it doesn't matter. Now you will do which one first, it doesn't matter. For the backwards elimination, all right? But for the forward elimination, it's meaningful. The sequences is meaningful for the forward elimination. For the forward elimination, you need to include the most significant first, and then the second most significant, and then compare between the most significant and the second significant. So it's different. It's different but similar. It's different but similar. Different way to start up, let's say. Yeah. Yes, we compare with the full model. Yes.
The full model again and estimate again for.
No, not necessarily. Once you run at the beginning, and that's data stored under your name, yeah, under the name that you specify at the beginning. But make sure that you pick the right one, that is the full, if you call full, right? And then you no need to run every time. You just run the reduced model straight away. That's why we need to take the benefit from estimate and store. All right, estimate and store. Okay, and tell me which variable can be omitted. 6? Only 6? So the concept for prediction model is that we don't need the models now being too complex. We don't need too complex model. We want simplified model, not too many, but not too small. Not too many number of covariates, but not too small either. That is the concept of prediction model. Okay? But here we don't want to build a prediction model, but we want to assess now which factor associate with treatment allocation. All right? It's another aim, but now we just want to make sure that the model selection is valid. So we apply the concept of model selection to select the treatment model here. All right? Understandable? Shall we move forward? So the final model, the next round, this is still multivariate analysis. So can you please fit by including only significant variable into the final model? for this table that you can see the distribution, the unbalanced distribution of the covariance between last and non-last blockage. You can see that last blockage is younger and not less percentage of males, and now a little bit higher BMI, and also higher diabetes, higher hypertension, little higher CVD, and lower the LDL, right? Lower mean LDL, and quite similar for HDL and urine albumin protein group. Okay, so you can see from here that now the last blockage that has quite poor prognosis, now higher comorbidity, particularly for hypertension and diabetes and CVD, right? And also higher BMI. But that's only younger age. Just only younger age. So this is the way how to look at the data, and you can see that if you don't adjust properly according to this covariance, it might not be the effect of RAS blockage, because they are different at initial treatment. Okay? All right. So you come up with the last or the final model for the treatment, right? Final treatment model that consists of 6 variables: age, BMI, diabetes, hypertension, CVD, DLDL. Keep this in mind. This is the way how to now create the treatment model. Okay, and then the outcome model. The outcome model. So the outcome here, the outcome now is, I think it's the event 2. Can you tabulate the event 2? So in total, now 26.9% of the patients that develop now ESRD, event 2. Okay, can you please tell me how difference between the last blockage and non-last blockage? This is cumulative incident, all right? This is cumulative incident. Can you please tell me how they are different, the rate now of ESRD between the two RAS and non-RAS blockage group? The same, this table, but don't add the outcome into the same table, that baseline covariate, okay? When you report, because now they are different sequence. This is just baseline characteristic between the two treatment group. But for the outcome, you have to separate another table. Now, suppose the table 2 for the outcome, it should be, all right, the same as this, but you just change the heading to be ESRD and non-ESRD, okay? That is universal for the outcome, all right? So the next table 2, it should be the characteristic of the patients according to the outcome of interest, ESRD, positive, ESRD, negative here, all right? I delete this, okay? And ESRD. And then treatment, there is study factor of your interest here. And then you need to add the first, I prefer to report the study factor first, the treatment. RAS and non-RAS. Okay, and then you display the number of RAS in ESRD and non-ESRD and non-RAS ESRD. Okay? Clear or not clear? So the table should be something like this, that all right. Okay, let's hit the command in Stata if you want to lay out this way. Okay, hit the command in Stata and lay out exactly this way, please. And tell me the percentage. Which percentage? Which percentage? Another way around. Another way around. There is nothing wrong, but if I want to lay out this way. Another way around. Another way around. Yes, another way. Lay out another way, exactly the same as that. There is nothing wrong at all. Okay, there is nothing wrong at all. But if we want to lay out this way, and tell me the percentage. Row or column percentage. Now another way around. No. Yeah, you're right. You're right. Yes. Yeah. Can I have a look at the command again, please? Okay. So the percentage by. No, this is incorrectly. It's correctly, but if you want to lay out on that way. Yeah. Yes. Yeah, the event lay out on the column. Yes. And now the RAS package. Now on the row. So the outcome variable event 2, not event 1. Event 2, okay? Event 2, not event 1. And so tell me the row percentage or the row column here. We want to estimate the rate of ESRD between the two treatment groups. We don't want to estimate the percentage of RAS blockage between ESRD and non-ESRD. We want to estimate the rate of ESRD between the two treatment groups, right? If RAS blockage work well, so that we expected to see lower ESRD rate in RAS blockage compared to non-RAS blockage, right? So what the percentage? No, you can tell me. Yeah, I'm listening. No, you can practice. Yeah, it's not too bad. Come on. Yeah.
So ESRD with no use of the RAS is around
No. ESRD in non-RAS package. ESRD in non-RAS package.
in non-RAS is around 29. Oh, you use event too?
Yeah, I use event 2. Yeah, event 1, not ESRD yet. Please use event 2.
Event 1 identify that the variable. So I have to sorry.
Event 2 is that? Is it? Okay. Yeah, you may be right. Yeah, let me take a look. Yes. Yes, you are right. Event 1. Sorry, buddies. Yeah. Event 1 is ESRD and event 2 is dead. Okay, let's use event 1, ESRD. So what is the rate of ESRD in RAS package? $10.1, 10.2. Okay. Round up, 10.3. All right. And non-RAS package. $18.3. Okay, good.
Is the 89.7.
Well, it must be 100%, right? According to the rule, right? According to the rule, it must be 100%. Okay? It must be the percentage of the treatment. All right, and then we need to test the null hypothesis. Yeah, that is now the rate of ESRD in RAS equal the rate of non-RAS ESRD. All right. Why? Yes. Why? I don't know. Do you use the same data? The same data? RAS and event. Well, what the percentage do you want? Yes. Yes, but here that you lay out row and column, right? Row is the treatment, right? And the column is the outcome, right? And then you ask for the column percentage, right? You ask for the column percentage. So 100% must be according to the treatment, not the column, not the event, okay? Because this is the study design as the cohort study. The cohort study that we started from exposed and non-exposed, and then ESRD occur later. Okay, that is typical cohort study. Whether it's prospective or retrospective cohort study, that we started from exposed to disease occurrent. So that's why we need the percentage of the treatment group, not the outcome. Okay? Not the outcome of interest. You need to understand more and more about the study design for the augment. This is just basic epidemiology. Otherwise, you want to be able to analyze data for your thesis. Okay. So right now that we can see that the differences of the rate here. The point estimation, 18.3 versus 10.3%. And should be very highly statistically significant different. This is from univariate. But we knew that because characteristics at the baseline are very much different. This is poor prognosis, high DM, higher hypertension, higher CVD, higher BMI, just only younger age. That's all. So it might be due to baseline characteristics at the beginning rather than the treatment effect. All right, so from here that now the treatment group is 10% and the non-treatment group is 18%. Even though this now having higher DM hypertension CVD, but this is older, might be due to age. Even though these characteristics are much different, but anyhow it's confounded by these factors. Okay, so let's do univariate and multivariate of the outcome model, please. Step by step, as you just have done for the treatment model, and tell me what is the final of the outcome model. Okay, let's do univariate and multivariate in order to the final model, find the final model for the outcome model. Okay, do the same as you do treatment and the same covariates here. The same covariates, but you do according to ESRD, event 1. All right, and do step by step for univariate and tell me what variables should be included in the multivariate and what now variables now should be remained now in the final multivariate model. Okay? And then we come up with the final outcome model. We just work for the final treatment model and then we incorporate them into the treatment effect model. Okay? And you can go to the toilet during this time. But if you don't want to, you just try to finish the outcome model and then we combine the two models together. Yes. You did about event 2 previously or event 1? Event 1. Yeah, it must be event 1. But previously we did for the treatment model. You have to do the outcome model here. The outcome model.
So I mean, the same model but change to the outcome. Change the outcome only.
Yes.
But use the same variations.
The same variables, but you need to go to no. You need to do univariate because here previously we work on RAS and non-RAS, but here is ES. Yes, repeat it again. RAS But here is ESRD versus non-ESRD, okay? So that might be significant for some covariates. So previously now we omit DHDL and urine albumin, right? But DHDL and urine albumin might be significant for ESRD outcome, okay? You have to repeat model selection. Okay, tell me what variable should be included in multivariate outcome model. Yes, of them. Yes, definitely. Yes, yes, yes. You have to redo because previously we worked on the treatment model. Here is the outcome model. You have to repeat the same process. For the table 2. Table 2, that is ESRD. For the table 2, univariate analysis of the outcome. All right, you have to redo. No. Actually, it is table 2. Table 2, the outcome model. Okay. Yeah, I think you understood correctly. Yeah. But here is the table 1, but you just change ESRD, not the last bucket. But when you report, that is the table 2, not the table 1. Okay. Or it can be table 3. This is univariate of the treatment model, table 1, and multivariate of treatment model, table 2. Okay. And then table 3, ESRD, univariate of ESRD, the outcome model, and then multivariate of the outcome model. Okay, have you finished the outcome model? So what the variables now should be included in multivariate model?
It's not significant. It's like 0.14.
Okay. Okay. So
It is the event one.
yes. So age is not significant. Gender is significant. BMI. DM. CVD. DLDL. DHDL. Yes. And urine albumin group.
Yes.
All right. Collect them to multivariate analysis, please. And then select model the same. And tell me now which one should be now included in the final outcome model. Yes. Yes. Yes, yes. Likelihood ratio test. Okay, as I just mentioned previously that when you do model selection, model selections that mean that we consider which variables should be included in the final model. Okay, that's the concept for working on prediction model. For the last bucket, yeah. For the treatment model, yes. Not significant, yeah.
Pair by pair, they believe each one in this model.
Yes, yes.
Therefore, I compare each one to the model that
Omitted CVD, yes. Yes. Omitted, yes. Okay, yeah, that's I explained previously that now there are two tests. Now the first one that likelihood ratio test that you have done, and the second one, this one that we call WALT test, this WALT test. Okay, and both tests now do the same now hypothesis, test the same hypothesis, now hypothesis. Now whether now gender now that is the differences between male and female, the coefficient here. The coefficient here is equal 0 or not. All right. Okay, the question is not clear about now why do we need to do good likelihood ratio test? Why won't we just use the test in the regression table straight away? The test in regression table that we call what test? What test? Okay, actually it's the same aim, In the regression table for the world test, for example, the null hypothesis, the beta for male versus female, right? The beta coefficient equal what? When we test the beta coefficient, equal 0, right? And then we apply the test, normal equal the beta hat divided by SE. Okay? From the regression table. All right? Which is the same aim. Now, if we now do for the likelihood ratio test. For the likelihood ratio test, the LR equal minus 2 the LL reduced minus the LL full model. The log likelihood of that full model with gender and omit gender. Okay. So that whether gender is significant associated with treatment allocation. The same meaning as this. If this is equal 0, so that means the beta coefficient correlation, beta coefficient is the coefficient of correlation between gender and treatment allocation. So if it is 0, close to 0, and that p-value is not significant, and that should correspond to the likelihood ratio test. So you can use one or another. But the problem is that the world test is not sensitive. It is not sensitive. So if you want to build up valid model, particularly for the treatment, for the prediction model concept, and that you want to build a parsimonious model in order to predict the event of interest, so that you may have to make sure that the model is valid, that based on a good selection model. Okay, so that's why we apply likelihood ratio test. We won't use the world test for model selection. All right, but actually both are the same aim. Okay. Okay, so for the final model of the outcome, model. So we should, now is there any variable from this that can eliminate from the model? Hypertension is not significant? All right, so therefore you have 7, right? Okay, keep in mind that the outcome model consists of gender, BMI, DM, CVD, DLDL, HDL, and urine albumin. So keep this, that we have the treatment model and we have the outcome model. And as I mentioned at the beginning, that for the treatment effect model, there are many approaches, and depends on which approach that you want to work on. The first approach we call regression adjustment. The regression adjustment, the first approach, or RA, instead of command. RA, regression adjustment. This is about the outcome model. So you just pick what you have done for the outcome model. All right. If you now select inverse probability weighting, IPW. This is the treatment model. So you select the treatment that you just selected. All right, that is the concept. If you use doubly robust treatment effect model, combine regression adjustment with inverse probability weighting, so you have both treatment and outcome model. Okay? All right, let's start with the regression adjustment. Let's start with regression adjustment. For the regression adjustment model, that now we need now only the outcome model. Only the outcome model. So the layout now of this command is that you need to now work on the TE effect. That is the command, the treatment effect. T effects. That is the command. Follow with the approach that you want to use. Here is regression adjustment, RA. Okay. And then follow with the outcome model. So the layout for the treatment effect here, normally we have TE effect. Follow with the approach RA. And then the outcome model. And then the last two. This layout. Okay. This is the command. This is the approach. Also the command. And this is the outcome model. And then the variable of the treatment. Because regression adjustment is the outcome model. So how it works for regression adjustment? It works now with the treatment model that you just selected. But you analyze that based on the treatment number 1 and the treatment number 0. Okay. If you want to do manually, you have to do something like this. But now you can use ready-made command TFX. Follow with RA, regression adjustment. And follow with the outcome model that you just have done. All right. And then you have to follow with the treatment variable. And here that the outcome is yes or no, ESRD or non-ESRD. In the outcome model that we just applied the logistic equation, right? You can use Probit equation, you can use Poisson equation, but here we use logistic equation. So you have to specify now in the treatment model. You can see from here that I specify comma logistic. If you don't specify, the default is Probit model. Another link function, not logistic link function, okay? Another link function. So collect the outcome models from that you have just done and add into this command, all right? There is no model selection here. You have to do ready-made. Now prepare for, collect for the outcome model first, and then you can add into here, okay? And then you can enter. Okay, you can fit as continuous variable or you can fit as the dummy variable. If you want to, okay, BMI. Yeah, you can fit BMI as continuous variable or categorical variable. Previously that we fit as continuous variable. Oh. Okay. Previously I worked on categorical variable. This is okay. We can work on here that DL. LDL. But if you want to categorize the variable, you can do as well. Yes. Okay. เขาดูหน่อยว่าโมเดลที่ omit hypertension อยู่ไหน
อันนี้คือ hypertension
ไม่ข้างบนไหนโมเดลไหนที่ omit hypertension อันนี้นี่ไง hypertension อยู่นี่ไง
ค่ะพอดีมาก็เทียบพอดีเมื่อกี้เห็นอาจารย์ไม่ได้ใส่ hypertension เข้าไปอันนี้คือ without hypertension
เดี๋ยวขอดู without hypertension ก่อนอันนี้คือ without hypertension เนาะนี้ HDL LDL CVD DM โอเค omit hypertension ค่ะ แล้วก็
run LR test
run LR test
ระหว่างอันนี้คือมีอันนี้คือไม่มี
โอเคขึ้นไป full model แป๊บนึงอันนี้คือ full model เลื่อนลงหน่อยโอเค hypertension significant นะ Okay, for the outcome model that you said that hypertension is not significant, but it is significant. Are you sure? Not significant? Why you come up with it different? Okay, let me check. Log it event age, DM, hypertension. Have you had treatment as well? The hypertension is not significant? Okay, it depends on whether you add. I think you add the RAS blockage, right? You should not add the RAS blockage. Yeah, omit the RAS blockage. Yeah. the last, the treatment. Okay. All right. Now, once you run regression adjustment, you can see from the output here that is estimate potential outcome mean. Now, in the control, okay? In the control. And also estimate average treatment effect. So, the average treatment effect equal average treatment effect equal POM1 minus POM naught, right? So POM1 equal average treatment effect by plus POM naught, right? So can you calculate for me? Well, after we select the outcome model, right? So that the final. Did I? Did I have H as well? So you remove H, please. Yeah. Okay, this one. Your final model, let's say, your final model. So the way to calculate POM1, yeah, I think it's another way around. Now POM, average treatment effect equal minus, right? And then POM naught minus POM1. POM naught is another way around. POM1. And then POM1 equal POM naught. Okay, POM1 equal POM naught minus average treatment effect. Right. So the POM naught should be lower than POM1 should be lower than POM naught. Another way around. Yeah, it did correctly previously. Sorry for this. Average treatment effect now equal this POM1 minus POM naught, and that plus POM naught equal POM1. Okay. So what we have to do, LinCom. But before you work on LinCom, can you do again page up command T effect, okay, T effect, and then add coef agent. It's not allowed. Yeah. It's not allowed. Anyway, yeah, that's all right. A very simple way that you can do here. Okay, let display underscore average treatment effect. Okay. All right. Let's do this way. Option POM. Okay, option POM. And then you can see that now the POM now for the treatment group, RAS blockage is about 9.8%. And it is about 18.1%. So subtract the two of them equal average treatment effect, okay? So if you copy, display this minus, that is POM1 minus POM0, it is minus 0.83, and that equal to average treatment effect, okay? So what we need to estimate here, if you want to report here that you said, so the risk now of ESRD is about 9.8% now in RAS blockage, and it is about 18.1% in non-RAS blockage. And now the average treatment effect is 8.3% lower. 8.3% lower ESRD, significantly lower ESRD in RAS blockage compared to non-RAS blockage. And the 95% confidence interval approximately about 9.1 to 7.5% lower. Okay? That is the average treatment effect. So the way it works, that this regression adjustment, we run ESRD stratified by the treatment 1 and 0. And then we predict the probability of having ESRD in the group 0 and the group 1 and subtract, and that is average treatment effect. That is the way how to do. But we just use the ready-made command from here. So the next method that is quite popular and we apply a lot is inverse probability weighting. The inverse probability weighting, from here that you can work on the inverse probability weighting. So the inverse probability weighting based on the treatment model only. Okay, based on the treatment model only. So when we work on the treatment model, and then you have to select the treatment model upfront before you applying this method. And that include not only the significant variables that associate with treatment allocation. So the way to work on this, that the layout is quite similar to what you have work on for the RS command, the RA, regression adjustment. But here that you need to now work on the treatment model. So the first abbreviation now for this that TFX and then inverse probability weighting IPW. And then the first layout that is the outcome model. No, sorry, the outcome variable, because this is the treatment model only. The outcome variable, and then the next is the treatment model. So for the treatment model here, that you have to work on RAAS2, and then along with the covariates that you have been selected previously for the treatment model. For the treatment model, that you have age, right? And next you have gender or not? No gender, BMI. And what else? DM, hypertension, CVD, DLDL, no HDL, no urine albumin, right? Okay, good. Shall we start with POM? Potential outcome mean or the risk of ESRD. So you can see it's a little bit different between the two techniques. So for this technique, now how it works for this technique. So after you now come up with the final model, but final treatment model, after that, now when you work on the treatment model, and then you can predict. So how it works for this one. So you have logit now of RAAS divided by 1 minus RAAS. Now equal beta naught now plus summation now BI XI, right? And XI that you have 7 variables from here. Okay, and then after you run this equation, you predict, use command predict PS, that is propensity score or the probability, the same meaning, okay? After logit equation, and then you can predict probability from the logit equation. The post estimation command of the logit equation, and then you use the predict command. So predict probability. So predict with our option, that is predict probability. Probability here, that is probability of receiving last blockage. And 1 minus P equal not receiving last blockage. Okay? So probability or the propensity score is the same. So the way after you estimate P, and then you generate, then you build up the outcome model, right? So the outcome model here, logged it. ESRD 1 minus ESRD equal beta naught plus the treatment, that is last blockage. Okay, and this is weight. 1 minus PS if the treatment equal, if the treatment RAS equal 1 and weight equal 1 minus PS if the treatment RAS equal 0. Okay, so that is the way how it works in inverse probability weighting. So you can see here that the outcome model, very simple, contain only one variable, the treatment, contain only the treatment, not other covariate at all. But now you need to weight now with 1 over PS for the treatment group and 1 divided by 1 minus PS for the non-treatment group. That is how the inverse probability weighting works. So that's why we call the treatment model. But make sure that the treatment model is valid. And then we will assess how valid it is later. Okay? So for the inverse probability here, that based on the treatment model, and you can see that now the risk or the potential outcome mean now for the treatment group equal 10.1%. And it can vary from 9.5% to 10.7%, quite precise estimation here, from 95% confidence interval of potential outcome mean. And the risk of ESRD for non-RAS blockage are 19.3%, and 95% confidence interval vary from 18.6 to 19.9 or 20.0. Okay, and if you subtract the risk of ESRD 19.3 with 10.1, and that should be the risk difference or average treatment effect. Okay, average treatment effect. From this equation, if you request with the option coefficient, and Stata will provide you the name of the coefficient here. You can see from this table. Instead of providing the full function of the test and 95% confidence interval, but you can work from here. For example, if you want to subtract the 2 POM along with 95% confidence interval, you can use LINCOM. LINCOM, that is linear combination. Linear combination. And that is the coefficient of the group 1 minus the coefficient of the group 0. Right? And then enter. And that equal to average treatment effect. All right? But here that we want to look at the ratio, because the ratio, that is the ratio of the two potential outcome means. And that we call the ratio, the risk ratio. Okay, if you want to estimate the risk ratio, you can't use linear combination because linear is linear combination. The ratio is not linear combination. So you need to apply non-linear combination NL-com. And then you can name like now risk ratio. Because we want to estimate now the risk ratio now equal POM1 divided by POM0 here. That is the risk ratio. Okay? So POM0, that is the beta coefficient here. And POM1, you just copy now the beta coefficient. I just copy from here, or you can type, but the more you type, the more error you are. And then enter. All right. Then we come up with the risk ratio. So what does it mean for the risk ratio here? Can you interpret the risk ratio for me? You missing the parenthesis. Yeah, the parenthesis is unbalanced. You have the open round bracket here, but you don't have the closed bracket. Yeah, that is the meaning. Okay, good. Is unrecognized command NC, no NC. Non-linear, NL. All right, can you interpret the risk ratio of 0.52 along with 95% confidence interval of 0.49 to 0.56? Patients who last blockage, lower risk of ESRD compared to non-RAS blockage treatment. How low is low? Uh, 47.8% lower ESRD in last blockage compared to non-last blockage. Can you say again nicely?
Patients who have received RAS blockage have 47.8% lower risk of ESRD compared to non-RAS.
Whether it is significant or non-significant here.
Significant. It doesn't include.
Okay. Okay, can you say again with significant as well? The patients who receive last blockage have
(46 to 52% of lower risk.
okay, that how precision, right? How vary of the risk? How vary of the risk? About 44 to 60 to 52, 44 to 62. So the patients who receive last blockage now have significant lower risk, about 48% lower compared to the patients who did not receive last blockage. And the lower risk vary from 40 44 to 52%. Okay. So that is the risk ratio. We also have the risk reduction, that is average treatment effect, right? Okay. Shall we hit the command and then, or we can work on this? Yeah, we can work on, we just work on Lincom, right? Can you copy Lincom again, please? Or page up Lincom command? It should be this one, actually, sorry, non-linear combination. So when you work on Lincom, and that the difference is or average treatment effect is minus 0.091, right? That is the risk difference. The risk difference. So can you estimate number needed to treat from the risk difference? So how we can estimate the number needed to treat? NNT equal 1 over absolute risk difference, right? Can you do this? Along with 95% confidence interval? Use NLCOM. Use NLCOM. Okay, from here, NNT, right? And then you subtract equal 1 minus absolute ABS. It should be something like this, I think. Yep. Hopefully. Yes, it is. Okay. One divided by absolute ABS, that is abbreviation of absolute. And then in the bracket, potential outcome mean of number 1 minus potential outcome mean of number 0. Right. And come up with how many? To prevent ESRD 1 patient. You come up with 10.9. So what does it mean here? Round up. With the number, yeah, just number. Round up. What does it mean here? Okay. Okay. Yeah, a little bit different, that is okay, but you just find out how you come up with different coefficient here. The model might be different, but you know the concept, okay? All right, what does it mean for NNT about 11, right, 11. So how can you interpret this finding? ESRD. Yes, ESRD, yeah. End-stage renal diseases. So if we treat the patients, 11 patients, and then we can protect 1 ESRD, okay? And that the 95% confidence interval that we may need to treat from 10 to 12 in order to protect 1 ESRD, okay? We may need to treat the patients with ESRD now 10 to 12 patients now in order to protect one ESRD. And if we treat 100, if we treat 100 patients, so how many you can prevent? What are 95% confidence interval? You need to multiply by 100 in our NL count. Multiply by 100. So if we treat about 11, we can protect one, right? If we treat 100, how many? But we do need 95%. No, not just display. So page up NL-com, please. Page up NL-com and multiply by 100. Yeah. After the absolute, 100. Might be something error for me. Yeah, I think. No, it's not multiply. Yeah, it's not multiply. So if we treat 11 patients, we can protect 1 divide by 11 and then multiply. If we treat 100, right? Multiply by 100. Okay. So it should be open the bracket from here and multiply by 100. No, sorry. It must be 1 divided by this and multiply by 100. Yeah. Something wrong. Something wrong. Anyway, yeah, let me figure it out. This is right 10 and then we divide this by 1 divided by this and multiply by 100. 1 divided by this. Yeah, this one. We can protect about 9%. Okay? Previously, we worked on the outcome model only, and then the treatment model only, and then we combine them all. Now, inverse probability weighting with regression adjustment. Okay, 2 in 1, which is the most robust model. So from this model, we estimate the treatment model properly, but for the outcome model that did not include the covariance in the outcome model, if it is inverse probability weighting only. For the regression adjustment, now we include the covariance on the outcome model only. but not for the treatment model. But here that we are going to combine them all together. Okay, we are going to combine them all together. So what we have to do that we need to apply inverse probability weighting with regression adjustment. So you paste up the command TE effect, and then now you add inverse probability weighting RA. Okay, and then you add now the outcome model. For the outcome model that we have 6, right? We have SEC2 and we have BMI, right? We have BMI. What else? DM, not hypertension, right? CVD, DLDL. Oh. Urine albumin. Urine albumin GR. This is the treatment model. Albumin. And then the treatment model, the same. As we work on inverse probability weighting. And that 2-in-1 outcome and treatment model together, and then enter. So you do the same. If you want to look at the risk ratio, you can use nonlinear combination command. And if you want to estimate a number needed to treat, you can do so. Okay? But we have yet checked the assumption. The aim for working on treatment effect model now in order to balance the covariance between the two treatment groups. We have yet checked on that. So we will work on this together for the next section on Thursday. All right? And then we will go through all the assumption checking for treatment effect model. And after that, we can go to now how to analyze database on time to event outcome. Okay, time to event outcome. Time to death, for example. Okay. Any question before we finish today? Any question? I move slowly because I want to spend the time and make sure that you understood now what I mean here. On the 12th, Thursday, we will start 1:30, okay? 1:30. I might be late, but I will try my best because I have that faculty meeting in the morning. I would say that if you have too many covariates, like 30 variables, that it's okay when you stepwise, but you have to be careful. But if you have not too many variables, manually selection is better. Manually selection is much better. And most of the time that we just use the twice and then we we pass the stage for understanding, in other understanding the data, and you may come up with like a lot of missing value and omitted some patients, and I usually see that you come up with like 50% reduction of the sample size without notice at all. But if you work on delivery state by state and you understand and see how many patients have been omitted according to missing data, or even you can re-categorize that. Sometimes that the variable can have like 2 or 3 categories, and then you can combine them first. If you can see the distribution after, you can see yes, and you remove the variable and make sure that the distribution is so. Alright. It doesn't need time to stepwise, so you can do, but you have to plot this data. Yes. All right, shall we finish today, and I'll see you on Thursday at 1 p.m. Okay. Thursday. This Thursday in afternoon. It's on the 12th, 1:30 to 4:30. 1:30 to 4:30. But information is broken. Now we revise the schedule quite a long time ago. We finalized the schedule, but between department staff, educational staff, and the department might missing somewhere. Okay. But to be sure that whenever they come in the class, and then you please change the schedule for the next section. That should be this app. All right. Okay, thank you for your. I will see you on this Thursday. Okay. And if you have a question, you can discuss with me later. Right. Thank you.
สรุปว่าตรงหมายที่อื่นเข้าก็คือบายบายเดี๋ยวอาจารย์ผมจะหาเวลาไปที่ซึ่งไม่รู้วันไหนที่เราป้าบอกว่าเดี๋ยวจะแจ้งมาในไลน์คือตอนแรกเหมือนเขาบอกว่าจะส่งนี้คือเหมือนตอนแรกบอกอาจารย์แบบสลับกันแต่ว่าเราคงเพิ่มปัญหาในไม่เพราะว่าคือไม่รู้ว่าอยู่ที่ไหนเสียใจด้วยคุณไม่เราสิเป็นการเรียนก่อนแต่ให้เขาทำไมก็คือเช้าว่างเหรอไม่เช้าว่างมันก็ต้องมี